Hi everyone. This video is on the energy balance for higher geography pupils. We are going to look at what is the energy balance and how does it work. Before we get started, you should make sure that you've watched the heat budget video before you watch the energy balance video. In the heat budget video, we learned that 100% of the energy comes from the sun, and therefore it's really important for us to understand that the Earth has the ability to get rid of that heat back out into space. If it wasn't able to do that, then the Earth would just heat up endlessly, and that wouldn't be good for life on Earth. So now that we've understood that there is a budget and that some of the heat is reflected away and some of the heat is stored on Earth, we now need to ask ourselves, why isn't the amount of heat on the surface of the Earth equal? Why isn't it as warm at the North Pole as it is at the equator? And that might seem like an obvious question, but actually it's more complicated than it first appears. So that's when we need to look at an image like this. This shows you, in actual fact, this is a representation of heat around the Earth's surface. Let me explain how. Here along this axis, we have latitude, south and north. 0 degrees latitude would represent the equator. And at the equator, we have a surplus of energy. That means we have more than we need, and therefore it is warm at the equator. As we move away from 0 in either direction, we head towards 90 degrees, which is, in this case, the North Pole. And we have the South Pole over here. And in these locations, we have deficits of energy, less than we need, and therefore it's cold. Why do these surpluses and deficits exist? Well, if you've watched the heat budget video, you'll know that the energy from the sun is known as shortwave energy. And the energy that the Earth releases back out into space more slowly is called long-wave energy. Now, shortwave is blue and long-wave is red. Where the shortwave energy line, the blue line, is higher than the red long-wave line, that means more energy, more shortwave energy, is coming from the sun than the long-wave energy that the Earth is able to release. So more is coming in than is going out. And as a result of that, we have a surplus of energy, and the area around the tropics is therefore warm. In the from 90 degrees to around about 40 degrees, we have deficit areas where the amount of energy leaving the Earth's surface is greater than the amount of energy coming in, and that's why it's colder. And it's worth also pointing out that there is an area of balance as well. If you were asked to describe the pattern of the energy budget, you would describe where these areas of surplus and deficit and balance are. Make sure you quote how many degrees, north or south, the point of balance, deficit or surplus is, and to point out how many, in this case, watts of energy is being recorded at those locations. So as I've said, in the tropical zone, we have more energy coming in, that means more insolation, more shortwave energy, than outgoing long-wave radiation. And when we go polewards, there's a deficit of energy because outgoing long-wave radiation is greater than the incoming shortwave insolation. I'm using a lot of technical terms here, but really if you slow them down and just think them through, they're not that hard. But you will be expected to use the term deficit and surplus and to understand the terms short wave insolation and long wave radiation. If you don't understand these terms, go and rewatch the heat budget video that is before this one. So here's the exam question. With the aid of a diagram, explain what the tropical, why the tropical latitudes receive more of the sun's rays than polar regions. This could be 8 marks, 9 marks, 10 marks, something like that. And it normally offers you the opportunity of using a diagram. Certainly, most people choose to use a diagram. So here's the Earth, and I've marked on some simple little reference points. Low latitudes at the equator, high latitudes up near the poles. This curved black line represents the atmosphere that covers the Earth's surface. And these lines represent rays of sunshine, as I'll illustrate. Before we start, though, what are we truly trying to explain? We're trying to explain why there is a surplus of energy in this zone, the tropical zone, and why there is a deficit of energy here in the zone that heads towards the poles. So here comes some energy from the sun. Insolation, shortwave energy. The first thing that happens is that depending where the sun's energy hits, you'll notice that it hits a different surface area. So for example, here in the lower latitudes near the equator, the sun's energy hits a smaller surface area. If you don't believe me, you can draw this out for yourself and your diagram will prove it to be the case. Both rays of sunlight are equal widths, if you like, on this diagram. And you can see that even though they are equal widths, the one in the north covers a much greater surface area due to the curvature of the Earth. As a result, the sun's energy gets spread over a greater area. It gets kind of diluted, if you like, over a greater area, and therefore the heating of the Earth's surface is less intense. Here, the sun's heat and energy is concentrated onto a smaller surface area, and so the heating is more intense. The next easiest thing to say is you'll notice that the sun's rays have a shorter distance to pass through to reach the Earth's surface. If you compare this line here to this line here, you can see that that has to be the case. If you've watched the heat budget video, you'll know that the sun's energy is reflected by gas, dust, reflected by the surfaces of clouds back into space. The more atmosphere that the sun's rays have to pass through, the more opportunity there is for some of that energy to be reflected back out into space by, say, a cloud. So the depth of the atmosphere here is less, and so more of the sun's energy can reach the Earth's surface because less of it is reflected by clouds. And here there is a corresponding greater depth. The next most simple concept, kind of going in order of simplicity, is the angle of incidence. You'll notice that the rays of sunshine at the lower latitudes arrive almost at 90 degrees to the Earth's surface. They arrive directly, like a dart going into a dartboard. And so most of them are absorbed directly on the impact. Here, though, because of the angle at which the rays of light are striking our Earth's atmosphere, some of them are bounced off into space. A bit like on a snooker table, if you hit the object ball with the cue ball at an angle, the cue ball is going to be deflected off in a new direction. This is called the angle of incidence when we are talking about sunlight, and the angle of incidence means that some of the sunlight is reflected off into space in the higher latitudes. I'll just pause here momentarily just to remind you, there is a degree of language usage here which is really going to secure you your marks. So by knowing the term angle of incidence and being able to tie it together with the insolation, technical term, from the sun, strikes with an angle of incidence in the high latitudes, which means that it is reflected off into space. By tying together these technical terms, you will make your life a lot easier in scoring the marks quickly and efficiently. Okay, now I'm going to move away from the diagram for a moment to explain why there is a surplus of solar energy in tropical latitudes, and this is the exact question that we're answering. Because there are some more points that I want to give. We've already covered the equator covers a small the insolation at the equator covers a smaller surface area, so is more concentrated. And we've covered that the insolation at the poles is spread over a greater surface area, so it's less concentrated. We've covered the greater depth of atmosphere towards the poles, and we've covered the angle of incidence. You can see the degree of detail that I'm writing in here to form this model answer. What else can we say? Well, the planet has dark surfaces, such as rainforests. Rainforests therefore have a low albedo. This is a term we've covered in our last lesson on the heat budget. The albedo is the way we measure the reflectivity of a surface. So dark areas absorb heat. White areas like ice caps have high albedos and reflect heat. Some other labels which don't necessarily go on the diagram, which is why I'm dealing with them here, are that volcanoes, natural features of the Earth's system, release huge amounts of CO2, carbon dioxide, and also release heat directly into the atmosphere. These two factors also account for the heating of our planet's atmosphere, and they have an influence upon it. Now we're getting into the slightly more technical end of the answer. Before I do so, I would just stress that these first 4 points are your bread and butter. They're on the diagram, and the diagram will help you remember them, because if you've drawn the diagram correctly, they're kind of there in front of you. These next 2 points are relatively simple to follow. Due to the tilt of the Earth, because the Earth's axis is on an angle, the poles receive no insolation, no sunlight, for part of the year, and so for this reason they're very cold. And then finally, once we've established this fact, we get into truly technical terrain when we talk about the Milankovitch theory. Now I'm going to spend a couple of minutes explaining the Milankovitch theory to you in the next couple of slides, but I'll go through what the answer should look like first, which is a little bit about face, but nonetheless we are looking at a model answer, so we may as well finish it. Milankovitch obliquity, this term obliquity, means that the axis of our Earth wobbles. It has a wobbling motion, and it wobbles very slowly. And on that wobble, on a kind of 41,000 year cycle, it exposes the North and the South Pole to greater or lesser degrees of sunlight. And because of that, this causes variations in the albedo. So less or more light is reflected from the poles according to where the Earth's axis is on this 41,000 year wobble. Now, to score full marks, you really are going to have to reach this point in the answer, but to score passing marks, you would need to score this point. And that's a good thing to know. You can definitely ensure you've got a good understanding of these first 4. The next couple, the next 2 or 3 are fairly straightforward, but after that you're into the Milankovitch theory. Now, Milankovitch was a genius of a mathematician and realized a series of things were true about the movement of the Earth in space. He also spoke about eccentricity. We've had obliquity, now we've got eccentricity. And Milankovitch realized that eccentricity is when the Earth's orbit stretches in shape, and this causes the length of the seasons to vary, leading to shorter or longer summers. And of course, if you have a shorter summer, then less heat is being received by the Earth, and that affects the amount of energy that is being received. I think these last 2 points need further clarification. So, We'll start off with Milankovitch, the theory of Milankovich's theory, and it comes in kind of three parts. This is the eccentricity, and before we even get to this reading, you might just benefit from just watching this image. Over 100,000-year cycle, the orbit of our planet around the Sun stretches and changes shape. This is why our seasons are slightly different lengths, because it depends where you are on this oval orbit when at what point you're on that orbit when summer, winter, and autumn arrive, and that dictates why our summer, winter, spring, and autumn are actually not just equal lengths. The more circular the orbit becomes, the more this evens out. And when the Earth's orbit is perfectly circular, you would expect the seasons all to be equal lengths. The next part of the Milankovitch theory is obliquity. Now, as you can see, the axis of the Earth is at 23.5 degrees, I think, right now, but it varies. And it varies on a 41,000-year cycle between these degrees. Now, these variations have much to do with triggering glaciations, because if the North Pole is pointing slightly more away from the Sun, then it will receive even less heat from the Sun, and that can trigger colder winters and trigger a glaciation over a long period of time. And that's basically obliquity explained. The last one, if you've got a great three-dimensional imagination, you can imagine these all happening at the same time, remember, because they are all happening at the same time, is axial precession. And this one I'll speak about more briefly, mainly because by the time you've spoken about eccentricity and obliquity, you have definitely scored all the marks in the answer. But let's just be thorough. As the Earth rotates, it wobbles on its axis as well, and this is called axial precession. This is due to a combination of factors. For example, the influence that the moon's gravity causes on Earth causes it to have an oblate shape, a bulged shape at its equator, and that affects its rotation. Anyway, axial precession makes seasonal contrasts more extreme, and it cycles once every 25 to 26,000 years. Now, would you need to remember all of this? The answer is absolutely not. If you're very keen, learn all three. But what I would do is I would learn one of them. The Milankovitch theory and eccentricity is a nice easy one. If you were able to pair it with either obliquity or axial precession, great. But I wouldn't really demand that you learn all three. And if we just go back to the model answer, you can see here I've talked about obliquity and eccentricity. And in so doing, I have scored 9 marks out of 8. And remember, these questions can sometimes go for more than 8 marks, so it is useful for you to have this extra level of information as a security. Okay, that's energy balance explained. I hope that was useful. If you've got any questions, find me in class.